let's continue with our discussion on the basics of probability. Let's start out with the fundamentals of what exactly probability refers to. And a probability is some number between 0 and 1 that describes the likelihood that some event will occur, or that some outcome will occur for a particular event. And a probability of 0 means that the event will never occur, or cannot occur, it's not possible. Whereas a probability of 1 means that the event will definitely occur, or perhaps we could assume that it has occurred already, it's a given. Now, probabilities are such that the sum of the probabilities of all of the possible outcomes must equal to 1. So if there is an event that has some number of different outcomes, the probability of each one of those outcomes must sum to a total of 1, so that the event itself must happen. We just don't know which outcome it will be, but the fact that it will be one of those possible outcomes is a certainty. Therefore, mathematically expressed, we can say if we've got I number of events or outcomes that could possibly take place, well, the sum of the probability of each one of those outcomes occurring must equal a total of 1. And this is a very fundamental principle that's going to be very important for us as we get down towards doing inferential statistics, and even sooner than that, because an important rule that stems directly from this summation rule is something called the complement rule, which says that if we have an event A, well, the probability of that event A occurring and the probability of that same event A not occurring must sum to 1. So again, if there's an event A and it either will occur or will not occur, the sum of each of those probabilities of A occurring, which we'll call here probability of A, plus the sum of probability A naught, A with a horizontal line over it, it's called A naught. The sum of those two must equal to 1. Again, the assumption is that A either is going to occur or is not going to occur. So one of those two things must happen. So the total of those two probabilities must sum to 1. And we can turn that around and say that, hey, if I know the probability of A not occurring, I can find the probability of A occurring based on this summation rule by simply saying 1 minus the probability of A not to get the probability of A. So the two are complements. So this becomes the complement rule. And if we think back to the concept of Venn diagrams, we can see this illustrated here to the right. I've got my universal set, which is described graphically by the black rectangle. And inside of that are all my possible outcomes, my total probability of 1. Well, the circle represents A occurring. Everything outside of the circle represents A not occurring, A naught, as we say. So the sum, the total area of A and A naught, is my universal set, my rectangular box. And just to bring this more directly to mind, we could, as an example, say that let's assume that you must be either a Coca-Cola drinker, which we'll call A, or not a Coca-Cola drinker. Again, A bar. Sometimes we'll see it written this way, A-BAR, as opposed to A with a horizontal line over it, but they mean the same thing. So in our situation, for event A, we'll say you must either be a Coca-Cola drinker, event A, or not a Coca-Cola drinker, event A bar. So this leads us to the complement rule. Now, we can extend this because probabilities can occur or can be calculated or conceived for events in combination. So let's extend our example from the last slide and say that in addition to your, let me rephrase this. In addition to your preference of Coca-Cola, how about that? In addition to your cola preference, either being a Coca-Cola drinker or not, let's assume that each person must either be female or not. So we have two different events, A either being a Coca-Cola drinker, A, or not. And then gender, right, which will specify as being female as being in set B, or outcome B, or not female, which we'll call B bar. And we can display this, illustrate this by the two circles representing the two events A and B. And as we start thinking about these combinations, we'll see that there's some new terminology we'll run into. We'll talk about the union of those two events A and B, the intersection of those two events A and B, and a bit later on we'll talk about a concept called conditional probability, which is very broadly used to help us understand the idea of independence, whether two events A and B are probabilistically independent. But for now, let's just focus on the union and the intersection. We can think of the intersection of events, and for reference I've shown the little Venn diagram in the lower right, as being a situation where both A and B occur. So if we're thinking about the probability of being in that intersection, we're saying we're in the probability of A and B. So if you look at the diagram, the area that's highlighted with the little oval shape, the area where the two circles for A and B overlap, any observation that's in that overlap area is a person who meets the criteria of both A and B. For example, in this case, those would be people who are both a Coca-Cola drinker and female. And notice my stress both verbally and with italics here on the word and. When we talk about the intersection of two events or two sets, we're saying both have occurred. So both A and B have occurred. So again, we'd be talking about the probability of a person being both a Coca-Cola drinker and being female. And mathematically, we represent this using the symbol of the inverted U. So this is our intersection of A and B. Also, we can think of the union of two events, A and B. And here, I would be describing visually the area encompassed by both circles altogether, which of course would include any intersection that may take place. So anyone who falls in that set would be in either A or B. So again, if we're thinking about the probability of being in the union of A or B, it means that either A has occurred or B has occurred. Of course, the intersection falls in there, so or both. And again, based on our example here of A and B, this would mean the probability of being a Coca-Cola drinker or being female. So it would include Coca-Cola drinkers that are not female, some Coca-Cola drinkers that are not female. I would also include some females that are not Coca-Cola drinkers, okay, as well as the intersection of people who are Coca-Cola drinkers and female. And mathematically, the union is described as in this way, as the probability of A union, with the right side up, U, with the probability of B. So again, here we've just covered some more basics on probability, our summation and complement rules, and then the basic combinations of the union and intersection of two outcomes or two events, A and B.